All right.
No, go on.
This lesson takes a while, so let me roll, shall I?
Yeah, let's roll.
Okay, here we go. Okay. So alternating series are bound. Here it goes. There are two types of series for which we can typically find this out. What are they? Telescoping and geometric. Truth. Okie dokie. For anything else we want to sum for, we need to basically just use a finite sum as an estimator. So, say you had this alternating harmonic series that's chopped a little bit, and I wanted you to estimate S. Now remember, there's no subscript, then that implies the infinite, so yeah. With S3. So, S3. How will I find S3, please? 1/3, first three together, yes. 1/3 plus 1, or minus 1/4 plus 1/5. What is the common denominator?
20? No, never mind.
60, okay. So 3 you had to multiply by 4 and 5, so that's 20. 4 you had to multiply by 3 and 5, so that's minus 15. And 5 you have to multiply by 3 and 4, so that's 12. So our estimate is 17 over 60. We? Okay. Now, there's our estimate. Now certainly, I did not add all of the terms in that series. I used a finite sum to estimate an infinite sum. So I am leaving off infinitely many terms. By leaving off infinitely many terms, obviously I'm going to get error because I dropped so many terms. This error is equal to, now the error is the difference between the true infinite sum S and the partial S3. We? Are you clear? Let's go a little further, okay? S is the idea of a third minus a fourth plus a fifth, dot, 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 forever, yeah? And S3 is a third minus a fourth plus a fifth, but ending. We? So if I take all the terms and remove my first three sum, then the error is the sum of all the left-offs. So the error would be, do you agree that a third subtracts away, a fourth subtracts away, and the fifth subtracts away, and what's left in those absolute values is negative 1/6 plus a seventh minus an eighth forever. Infinite error, yeah? All right. Now that's also called the remainder. It's what's dropped off, a lot like in long division, which you took yesterday. Some of you did very well. The left-off terms are sometimes referred to as the remainder, sometimes the error. You'll see both. So if I asked you in the problem above to find R5, then that means the remainder or the dropped off if the first 5 terms were used. So the remainder, R5, is all the terms after the 5th term. It is not all the terms after 1/5. Okay. So, what does R5, or the remainder, or the first part of R5, come out to be? What? I will wait. So if I used S5, what would I go through? What fraction would be the last one I used? 1/7. Okay, if I used S5, I would go through 1/7. The remainder then is everything after 1/7. So again, what's the remainder? Negative 1/8 plus a 9 minus a 10, and so on. R5 then, or the remainder that you would get after dropping off the terms after the fifth term is that. You follow? All right, now, why can't we know the error? Why can't we actually know, why can't I tell you the error is this? Yeah, if I knew the error, then wouldn't I know the actual sum? And then you wouldn't be estimating at all. There wouldn't be any error. So, it's because if we knew the error, we would have to know the true sum. We don't have a formula for the true sum. Sum, which we don't know. Okay? All right, so when we talk about the error, we don't actually find the error. We don't say the error is this because we can't know it. But we can bound the error. You are able to say, I know my error is no more than this. That's the idea of the day, the error bound. Now we did error bounded trapezoids, and it's pretty common in higher level math to have an error bound. So you'll see this at least one other time in Lagrange. We'll talk about that. But while we can't know how much error we have, there is a way to know how bad the error can be, and that's the idea of an error bound. And again, although that's nice, I prefer to think of it in layman's terms as the error is no more than blank. Right? Now, how to find the error bound. This is pretty cool, actually. I love this. This is slick. To find out an error bound, let's start with the series where we do actually know the sum for. So this guy is infinite geometric, right? And we do know the true sum. What is the true sum? Is this converging infinite geometric? It is. And so the formula is A1 over 1 minus R. So what's the sum, please? Two-thirds, I heard, and I agree. Here, the sum, the true sum is 2/3. You follow? All right. If I used S1 to estimate, what is S1? 1. Perfect. The error, which is the difference between the true sum and our estimate, is, now we said the true sum is 2/3. And if we use S1, or just one term to estimate, then we get an error of 1/3. You follow? All right, now, what I want to do is tie this a little bit to the terms left off. We get that error because we're leaving off terms. So would you tell me what is R, if I just use one term, then what is R1, or the remainder, or all the stuff I'm leaving off? -1/2 plus a 4th minus an 8th plus a 16th, cha-cha-cha, yeah? Okay, now, I'll come back to that. Leave me a little space over here, okay? S2, what is S2? 1/2. The error here, then, would be the difference between the true infinite sum and my two-term partial sum. And the error then is 2/3 take away 1/2. Now I'm using absolute value because I don't care if it's an over or underestimate. I just want to know how much it's off. I don't care if it's under or over. So that's why the absolute value, don't sweat those too much. What is the difference? 2/3 minus 1/2? 1/6. Would you show me the remainder 2, or what are all the terms I left off there? Oui. Cool. Okie dokie. Um, this should be S3. And R3. Would you do that one for me? Just to make sure that you understand what you're doing. And so I can get a break because I'm doing all the work over here. Okay, are you down? All right, so our goal of the day is to kind of get a feel for what the error is like. And it's obvious, first thing off is the more terms we add, the less error is, yeah? I think that goes without saying. But in terms of tying it to the remainder, the remainder has lots of terms left off, obviously. But if we compare the error to the remainder terms, I don't even need to look at all of them. And I don't want to look at all of them because it's so tedious, it's infinite. So let's try and tie it to a little less. The error seems like it's less than just the first term. Don't worry about the negative right now, I'll talk about that in a minute. But would you agree the error there is less than just the first term and all the leftovers? You with me? And a sixth seems to be less than a fourth, and a 12th seems to be less than an eighth. So it seems like the error is less than, actually, well, that's what I hear. It appears the error in the estimate is always less than the absolute value of the first omitted term. And I don't even need to get into all the omitted terms. I could just look at the first omitted term. Now again, don't get me wrong. I'm not saying the error is the first omitted term. All this sum is a third. This whole sum is the error. But as far as an error bound, it seems like the error is no more than the first term left up. Yeah? Again, because a third is less than a half, a sixth is less than a fourth, the error of a 12th here is less than the first omitted term in eighth. Okay, are you with me so far? So there's my theory that I'm thinking like the error is no more than the first term you drop. Now let's see if this is just a geometric kind of byproduct or if this might hold true for everything. So if you get out your calculator here, you're going to need it. Let's look at this alternating harmonic series, right? We're not going to do any trade, but you can, sorry. I just wanted to warn you there in degrees, so, but I don't think it'll matter for today's lesson. All right, so we don't have a formula for this. Geometric and harmonic doesn't have, harmonic doesn't have a formula. The best we can do is estimate. So no formula. Playing around with this in my calculator, it's a fine line between getting cute and doing too many terms and locking up your calculator into a endless calculation. So I had decent luck with, let's use S of 10,000 to estimate the infinite sum. So would you find the S of 10,000? So just to review, I don't know if you need to review, but oops. When you go to do this in your calculator, the sum button is right there in that catalog menu by the 9, and the summation is right there. Choose it, and then fill in the details. N of 1, 2, and we said, did I say 10,000? Okay, and the formula, this does require that you can go from general form to expanded form. So So the denominator, let's start there. What's the denominator if we started at 1? N plus 1 or just n? N. Okay, so the denominator is n. The top, I need to get an alternating negative, so that's why I opened up those parentheses. It's going to be negative 1 to the outside those parentheses. What do I want to go with, n or n plus 1? N plus 1 to get a positive. Is that clear why everybody's saying that? Everybody understand? All right, so if you hit that, I hope it doesn't loop for me. I get 0.693. Cha-cha-cha. You with me? Okay. Just for the sake of, would you store that to A? It'll save some time. Okay, cool. So we've got that. We know we have a pretty good estimate for the infinite sum. 0.69. Was it 693 or 690? 3. Okay. All right. Let's use that as a stand-in for S. Okay. Now, my point, again, I'm trying to get at or investigate is when you use a partial sum, is the error less than the next term always? So if we used S1, what is S1? 1. The error is, how do I find the error in an estimate? Yeah, you take the difference between the true sum and your estimate. Now, would you then take S minus, gosh, it's so small. Would you just do 1 minus A or A minus 1? And again, I'm using absolute value. I don't care about the error or the direction. So I get an error of 0.306. You follow? Okay. Now, is that less than the first omitted term? What is the first omitted term? If I stopped at 1, then what's the first omitted term? Negative 1/2. Actually, I should say the absolute value of the first omitted term, which is 1/2. Wouldn't you agree that error 0.03606 is less than the first term I dropped, yeah? All right, let's do S2. What's S2? 1/2. The error then is S minus S2, or the difference between our A and 1/2. So A minus 0.5 is 0.193. Alrighty. And is that less than A3, which is to say the first omitted term, which is 1/3? Did it hold true? Okay. So it seems like we've got a theory that works. Would you do me one more again on your own, just to make sure that you're doing some of the heavy lifting and to verify our theory is working okay? 1/2 plus 1/3 is 3/6 plus 2/6, so 5/6. 5/6. Did you get 0.140? There, okay. And is that what I want to show that that's less than? A4, the fourth term, which is, oops, sorry, it should be the absolute value of A4, sorry. I don't care what the sign, the number itself. And so it does hold true. You down? All right, so it seems like our theory works for numbers, but that obviously will not make a math textbook if we say, hey, for these two numerical cases, it's good, so it's good for all cases. That's not proof. So let's talk a little more general proof, right? So here is the alternating harmonic. You see? And would you find the first 7 terms for me, please? Notice I started off negative here. Okay. You have those? Okay. This is what I want you to do then. Forget finding the first 5 partial sums. We're just gonna do a little visualization. So these are mostly gonna be negative sums. So you wanna focus on this 4th quadrant, okay? The y-axis, that's not a table by the way, these are axes. The y-axis is the partial sums. The x-axis is how many terms you decided to use to add, all right? So there is no 0th partial sum. You don't use no terms to estimate something. That's stupid. So instead, we start off with 1 term. When I use 1 term, what's my sum? -1. Now, you can make that the very lowest point because your estimates are only going to get bigger from there, I assure you. When you use 2 terms, what's your partial sum? -1/2. When you use 3 partial sums, what's -1/2 minus 1/3? -5/6. Now that's going to be below -1/2 but above -1. Do you agree? Okay. What about -5/6? Now tack on a 4th. -10/6 plus 3/6 is, oh, sorry, 12. Excuse me, -10/12 plus 3/12 is -7/12. I assure you that's a little closer to -1/2, but not equal to, it's a little less, all right? And then if I keep going, I'm going to gradually go in, up, down, and so on. Yay? All right. Now, the true sum is in here, yeah? Oops, I missed. I didn't draw my line very well. Do you agree? All right, cool. This is S. Infinite S is in there somewhere. All right, now, this is what I want you to do. Set up a whole bunch of inequalities. Between all the partial sums, S1 through S7, what's the very least y value? So S1 is the smallest. What's the second smallest? And by that I mean the lowest y value. S3 is next, yeah? But S1 is less than S3, which is less than S5, which is less than S7. What's the next thing I come to? S, true S, which is the red line. Then what's the next thing I come to? Okay, I've done this, I'm gradually moving up. Now it's S6, and then S4, and then S2. All right. You agree with my inequality string? All right, cool. This is where it gets cool. Let's just focus on S1, S2, and S. If I just took S1, S, and S2, then it would have to be the case that S1 is less than S, which is less than S2. Wait. Now my intention is to prove that the error must be less than the next term, right? Based on our number theory from previous, yeah? So how did I get error in S1, for example? What's error in S1? S minus S1. So to get error, oh, this is S minus S1. So how could you get that error in here? I want to get this in here, but by using good math.
Subtract S1.
So let's subtract S1 from each one. Subtract S1 from each. Now if I do, then I get 0 is less than S minus S1, which is less than S2 minus S1. I have to subtract it everywhere, right? All right, so cool. Now, If we clean this up, 0 is fine. S minus S1 is fine. But let's flesh out that S2 minus S1. Isn't S2 just the first term and the second term added? I mean, isn't that what S2 means? I add the first two terms. All right. And what about S1?
First term.
It's the first term. Well, if I clean that up, then that implies that the difference between the infinite sum and the first is, well, A1 drops out, and I'm just left with A2. The conclusion then is the error in using one term is less than this term 2. You follow? I'm going to skip this. And let's just go general in the interest of time. Generally speaking, looking at all this, if we were to compare sum 1 and sum 2, or sum 3 and sum 4, or sum 5 and sum 6, isn't the true sum always between the earlier one and the later one? All right. So generally speaking, we could say the true sum is between a nth term and the sum of the n terms and the sum of the what? And minus 1 or plus 1? Plus 1. One more term, yeah? All right. Now, if we were to then subtract s sub n, like we did above, then we get 0 is less than s minus s sub n is less than s sub n plus 1 minus s sub n. All right, which means 0 is less than s minus s sub n is less than. Now, the n plus 1 partial sum is the sum of the first term, the second term, continuing on to the nth term and the n plus 1th term, right? And the n partial sum is the sum of the first term, the second term, through what term? The nth term, yeah? And therefore, the difference between the infinite and a finite number, well, all the terms drop out except for the n plus 1th term. Now, I am doing, in the interest of time, a little fast and loose because when the sign alternates, I mean, if you're really a critical thinker, then you might say, wait a second, isn't 6 less than 7? So isn't it true that this, well, the negatives do present a problem, okay, because it does alternate sign. This only works for alternating. That's why the absolute value, okay? So the absolute value is to remove the possibility of, yeah, when it goes negative, things get all whacked. I don't care if the estimate is greater or less. It's just how much error. I don't care which direction. You with me? Mm-hmm. All right, then. Here's the big idea. If a series is conditionally converging, and which is to say that's alternating, actually, will you put here, this is also sometimes called the Leibniz theorem. If a series converges conditionally, then when the nth partial sum is used to estimate the infinite sum, the error in the estimate is no more than or less than or equal to the absolute value of the next term. Or you can say the first omitted term, if you like. That's alternating series error band. Now, if you write yourself a note here, it must converge, or otherwise the difference between a finite estimate and an infinite sum can't be bound at all. That's ridiculous. You would be infinite error. Okay, so if the sum is infinite, then this whole thing is out of whack. You wouldn't try to bound something that has an infinite sum. That's stupid. Okay, you with me? So you have to meet conditions of convergence first, or at least really quick. The good news is you don't have to do it very thoroughly. So here we go. Using the same series, which can I start at n equal 1, please? And was it negative 1 to the n or n plus 1? And over it, yeah? Okay. I would like you to, this is what a question often looks like. Show the error in S6, I didn't use a subscript there, sorry, is less than 1/5. Now, you first, on these you quickly generally meet the conditions. Unfortunately, you have to do it, but you don't have to do it very thoroughly. So, for example, you would say this series alternates, the limit of the terms is 0, and what's the last condition for conditional convergence? The terms get smaller, the next term is less than or equal to the previous term, right? So it must be the case, by this theorem, that in using S6 to estimate the true infinite sum, the error, or the difference between the true infinite sum and my estimate, must be less than or equal to A7, the next term. Okay, and I use 6 terms, and the error is less than the 7th. You follow? What is the 7th term? Absolute value. So 1/7, yeah? Now the question is, demonstrator, show the error in the estimate is less than 1/5. Well, I actually showed the error is less than 1/7. Is it therefore less than 1/5? Yeah. Okay. Typically, you would then, the quick is then you just say which is less than 1/5. But would you, for the sake of your notes, say by showing the error is less than 1/7, it must also be less than 1/5, because 1/7 is less than 1/5. Now, you might be thinking, why did they say 1/5? Well, this is very common. They'll throw some just arbitrary number in there that'll work, and you might not know where's 1/5 coming from. It's just something that's compares well to 1/7. They might have said 1/3, and it would still be true. You down? All right. Would you try one on your own, please? 20 minutes to take attendance. Police absences. Oh, I'm recording this. Hi, absent people. All right. Oops. Estimate first. Oh. Did I want to start this one? I wanted you to start this one. That's right. I'll fix it this week. So this is a big gotcha. So what is the fifth term? Is it 1 over 5 factorial?
No.
It's not. That's a bummer. What is it? It's 1 over 6 factorial. 5. Yeah, it starts at 2. So to get to the fifth term in the pattern, you have to go to the 6, yeah? Okay. So that said, your sum should be something like negative 1 over 2 factorial plus 1 over 3. Oh, maybe we should practice some skill. How good at you are at factorials?
Pretty bad.
Okay, well, you need to be really good. So let's talk about how you would do this without a calculator. So, do you agree the common denominator would have to have all that stuff in it? Which is to say it's 5, 4, 3, 2, 1. So, the 2 factorial, what did it not have? Negative 5, 4, and 3, yeah? The 3 factorial, what did it not have? 5 and 4. And what did the 4 factorial not have? The 5, and what did the 5 factorial not have? The 1, okay. So you would typically look at it that way. 5 factorial, by the way, is 120. And so we get something like negative, 60 plus 20 plus, minus 5 plus 1. What is your S4? Negative 40. Negative 40, negative 45, negative 44? Oops, I made a mistake. Negative? Say what?
Is it 5 factorial doesn't have a 1?
Sorry, 5 factorial, we didn't need anything. How's that?
Okay, yeah.
Okay,
What about
there.
the first one? Mine's
Sorry, I misspoke. So, what'd you get there? Negative 44 over 120. Shall we reduce or say, ah, that's good enough? All right. Now, that said, proving the error is less than 1/500 requires you to use the Leibniz theorem. The conditions have to be met before you do. So the series is alternating, the terms go to 0, and the terms decrease. I don't have to get into those in detail, like I'm proving conditional convergence, thank goodness. You just state they've been met, and the reader takes your word for it. You with me? You should actually check that they're being met. Is this alternating?
Mm-hmm.
Do the terms go to 0? And do the terms get small in absolute value? Yes. Okay, so here we go. The conditions are met, therefore the error in using 4 terms is less than or equal to the first omitted term, A5. And what is now that you have this expanded, it's easy to see what the first omitted term is. What is it? 1 over 6 factorial, which is 1 over 6 times, where we left off, that's 1 over 720. Is that less than 1/500? Yeah. 1/720th is less than 1/500. Do you follow? All right. Now, I'm going to change this to 1 real quick. Yep, sorry.
Then why didn't you find us a photo?
Why did we or why didn't we?
Why didn't you?
There's the question. Yeah, I know in mine I didn't ask you to find the sum, sorry, but this one they asked, and so that's fine. Yeah. Okay. I don't want this to start at 2, so I know it says for the U try above, but I'm going to change it to a 1, just because I want to break this into more manageable chunks. I don't want to get too weird too fast. Keep the rest the same, and again, I forgot, is it to the n or n plus 1?
N plus 1.
Okay. And over n. All right, cool. So this is also common. Say you wanted to estimate an infinite sum. and they had some degree of precision involved. The person said, I want you to get the sum, and I know you're gonna give me an estimate, but I want you to give me a sum that's close enough so that the error is no more than 1/20,000. I want you to get the sum within a 20,000. Well, the first thing you would have to do then is figure out, all right, well, how many terms will I need to add, yeah? So, we need to really figure out, well, how am I going to do that then? I need to figure out how many terms I need to add. So I need to get my error less than 1/20,000. So what should I do? Yeah, I need to find a term that's less than 1/20,000, right? And if I find a term that's less than 1/20,000, then surely the error of all the terms before that would also be less too. Okay, so you need to find a term, a next term without sign, so that the difference between some number of terms in the true sum is less than that term, and that term is less than 1/20,000. And by doing so, won't I be finding error less than 1/20,000th as well? Okay, so I need to find that a sub n plus 1. Now let's start here. If I take absolute value of a sub n plus 1, then the negative 1 thing is not my problem. I just need to focus on the factorial, right? So I need to find what makes this true. What kind of term in the list gets me there, yeah? This will be handy for your notes. Would you go off to the side here and make a, just like your multiplication facts, you need a factorial facts. What's 3 factorial? 6. 4 factorial. 5 factorial. 6 factorial. 720. 7 factorial. So take 720 times 7. 4,900 and 140, so 5,040, yeah? 8 factorial, so take that times 8. What's 5,000 times 8? And 40 times 8. 40,000, what'd you say, 320, yeah? You probably could use 9 factorial, but that's okay. All right, so it looks like, which is the first n plus 1 that's beyond 20,000? N plus 1 needs to be 8, yeah? Now, if n plus 1 is 8, then n needs to be 7. Great. So does that mean then that or my conclusion is then that I need 7 terms. I need to add the first 7 terms to get error less than 1/20,000. Now, if they actually asked me to find a sum so that error is less than 1/20,000, then I would actually have to do that sum. But they didn't. Yes?
Where do you get the n plus 1 factorial on the bottom?
That is the n plus 1th term is what you get when you put into the term formula n plus 1 in place of it. Yeah? So it's plugging it into this, for this problem, it's formulas, series formula, yeah? Do you feel like you can do one on your own, or you want to try one together? All right, so here we go. Say you're estimating this guy, and although it's gotten it in the numerator, the geometric or exponential n in the denominator will win, so it is going to converge, yeah? But I do need to say it. This is an alternating series. The limit of the terms, do you agree the terms go to 0, or do you want to fight me? All right, and the terms will get smaller and smaller, at least at some point. There is an end at some point where they start to get smaller. They might actually get bigger temporarily, but as n gets infinitely large, they'll get smaller. All right, so it must be the case that the error bound formula is applicable. And I need to find a term that's less than 1/400th so that all the terms before it would add to an estimate that's less than a 400th. Yeah? All right, so now what do we do? So yeah, now you get into what is the n plus 1 term. Forget this for a second now. Now I need to find a term that makes this true. So what a sub n plus 1 is what? N plus 1 over 2 to the n plus 1 less than 1 over 400. Now, this algebra is pretty icky. And in fact, we don't even get into the algebra of it. For factorials, there isn't even an inverse operation for factorials, so that's a no-go. So this is done by trial and error. All right. Whether you cross multiply and solve this, or you just do it the way it is, the point is we need to, let's start by saying what is 1 divided by 400 as a decimal, because I'll probably be getting up. All right, so I need to get a term that's less than 0.0025, right? All right, so maybe we can use some number sense here. What about 2 over 2 squared? Is that going to be it? No. How about 3 over 2 cubed? 3/8. How about 4 over 2 to the 4th? That's not, I mean, that's not even close, right? Do you agree it's 4 over 16? That's 1/4. All right. 5 over 2 to the 5th? That's 5/32. Nope. 6 over 2 to the 6th? That's 6/64. 7 over 2 to the 7th. I wish I would have made the denominator a little more powerful. Oh well. 7 over 2 to the 7th. 8 over 2 to the 8th. I don't know. Let's start figuring this out here. So 8 divided by 2 to the 8th. What?
That's basically 2 to the 5th.
Oh, shucks. Yes, good point. 1 over 2. So we are not. Forget it. So we're not there yet. Should we keep going incrementally or just jump around a little? Jump around. How about that?
Yeah.
5 over 512. That's roughly 1/100. Is that there yet or not yet?
No.
No. 11 divided by 2 to the 11th. That's roughly 1/200. Yes.
Yep.
12 divided by 2 to the 12th. It feels like maybe I should have done this algebraically. That's about 1/300. Yes? 4, nope. 13's a yay? Divided by 2 to the 13th is approximately 0.001. Is that less than 0. What was the other one? 0. All right, is that less? Okay, cool. We're about to leave. Okay. So it seems like n plus 1 that worked needed to be, was it 13? So n needs to be 12. We would need 12 terms. You follow? Okay. Darn it, I didn't get to the last part. That's okay. Okay, I'll start with that one. All right, nothing to do. Have a nice weekend. Yes.
So, if they say that
Because it's really big terms that down, so you add all okay? You're welcome. Have a great weekend. Hi, absent people.